Hello students. So continuing our lectures on nanoelectronics, uh, we'll first try to understand what is the need for nanoelectronics. Like the current technology is primarily microelectronics. So why do we need a shift from micro to nanoelectronics? And the shift is mainly due to the fact that we are basically what we are doing, we are miniaturizing. We are into the process of miniaturization. Miniaturization, then we are into the process of integration. In semiconductor devices. Now, this need for miniaturization is due to a very well-known law called Moore's law. According to that law, the number of transistors on a chip will double every number of transistors on the chip will double every, I put it a blank, dash months. Now, why I have used the word dash here? Because this number is gradually decreasing. Right? Had it been 10 years, it would have been, now previously it was 1 year, now it has come to months. So this is the thing, this is the state, or this is the value which is gradually decreasing. That means the miniaturization or the doubling rate is becoming faster and faster as we proceed. Now, the current semiconductor technology is based upon something called a 45 nanometer rule. The Intel Core to Extreme processor this is the processor which is in use right now. It is of the size of 45 nanometer. So and secondly, the nano fabrication method nanofabrication method is again consists of using a photoresist. Right. You have a silicon wafer, then you have a photoresist at the top. You expose it to the light, and then you get the fabrication done on the surface of the silicon. So this is a basic standard nanofabrication technology that is into use these days. So this can again be a negative photoresist, it can be a positive photoresist. So depending upon the situation, you actually can form patterns on the silicon surface. This is how the nanofabrication is done nowadays. Now, the latest chips, the latest chips in the market. So we are basically into something called 14 nanometer Broadwell semiconductor chip. So and we also have something called cross section. We do the cross section of this chip. So we develop interconnects. It produces different chips or different dimensions, and it is called interconnect pitch. Now, the advantages of these basic latest chips are also very high. Like if you would like to see the product benefits in terms of product benefits of using these latest chips. So the performance has been found to increase, and the only thing that has decreased is the active power. This is where we need to work on. Active power seems to have decreased. However, the performance per watt has increased. Now these improved chips, for example, if we talk about fifth generation, now the seventh generation has also arrived, but let's consider which is in use. The fifth generation Intel Core processor it provides three-dimensional graphics, 22% increase, 50% increase in video conversions, and there is increase in 50%. Then there is battery life has also increased by 1.5 hours. So these are the areas where this fifth generation Intel process chips have shown an increase, and now seventh generation also arrived, which is even showing better performance. Now, what has been the difference between the fifth generation and fourth generation? So, if you consider the fourth generation chips, fourth generation Intel 4 processor chips, so they used to have uh, 0.96 byte transistors, in an area of say 131 millimeters square. Now, in case of fifth generation, I think that has improved is there has been a 35% more transistors, whereas the size in which these were enrolled has decreased, and 37% less size. Right now we have 1.3 byte transistors in an area of 82 millimeters square. So this has been the difference, and due to this we are getting a higher performance of this fifth generation. Now, the next thing that needs to be considered is the increase in the record density of hard disk drives. Similar to Moore's law, the areal density, areal density will also double in every, again similar to Moore's law, dash points. So this value is increasing dividing. So now a very significant development in hard disk drives has been the giant magnet resistance. After this values has now, it is not as serious as in the case of the chips. This value has shoot up little. Okay. Now, how do we actually record? We have, if you look into the structure of hard disk drive, so there always is ARM associated with the recording head. So this is actually the This is the recording head, and this is the arm. And considering a disk, like in the case of a CD, there is, we consider the disk rotation, say in this direction, then this is how it gets recorded into the disk. The interesting thing is the disk, what is the disk is made up of. So the disk has different layers, like it has got a lubricant of 1 nanometer. Secondly, it has a carbon port of say less than 15 nanometers. Then it has a magnetic media of say 30 nanometers. Then it has a chromium buffer of say 50 nanometers. Then it has a nickel buffer of say 10 nanometers. And lastly, it has a metallic or a glass substrate which has got no dimension, and this is how the rotation. Now the recording density of these disks it increases at 100% per year. The first hard disk drive is called RAMAC. Uh, 305, and it was in 1956 developed at IBM. The current hard disk drive, so the first we're talking about the current hard disk drive, is UltraStar DC HC 650, and it's in 2020. The difference between these two is the storage capacity, of course. This used to store the range of kilobyte per inch square, and its weight was 920 kgs, whereas the current one, it stores in the range of terabyte per inch square, and its weight is now 690 grams. So you can see how difference. So the magnetic recording technology nowadays is isotropic to giant band resistance. So the current magnetic recording is something called an isotropic to GMR. And the another thing is that we are shifting more from longitudinal to perpendicular recording. Now, what is the advantage associated with nanoscale miniaturization? So, advantages of nanoscale miniaturization. So the first thing that comes to our mind is the faster operation, and that is due to reduction of effective electron paths, and the second is reduction of electron scattering. These are the two reasons. There are two advantages associated with miniaturization, giving jet performance of the devices. Now, to understand nanoelectronics, apart from that, there are a few things like there is no joule heating associated with electronic devices. Secondly, no, there is no leakage current. There is no electron confinement. So there is a there is a leakage current. So there is a joule heating. So this has to be taken into consideration now. So people are working on it too. Since we have reduced it to very higher operation, so joule heating is a problem. Secondly, the fabrication cost is a problem. And since the fabrication is much more complicated. Now, To understand nanoelectronics, we need to have knowledge of few other aspects, like we need to have knowledge of electromagnetism, then we need to have knowledge of quantum physics, and we need to have knowledge of the nano device application. Now, considering the electron transport phenomena, in devices, in a nano device, the transport uh, or electron scattering is a very important has a very important part in transport phenomenon, electron scattering, and there is something called L, is known as the mean free path. That means the distance traveled by the electron between two scattering. Now, if the device or the device dimension is greater than L, then the chances of electron scattering increases. Whereas if it is less than the mean free path, then we would have negligible. This is the case, then this will cause negligible electron scattering, and also this can cause a transport which is equivalent to a transport in vacuum. And also the vertical dimension is of the order of the Fermi wavelength, lambda f. So L is the mean free path, and lambda f is the Fermi wavelength. Now, coming to the nano device structures, there are basically 4 fundamental nano device structures. The first one is called ultra thin quantum well. Ultra thin film, or it's called the quantum well. it is of the shape like this. Basically a thin film. Or you can have the second one is a multi-layer. Or you can also call it a super lattice. So you have layers of. So this is the first layer. Then there is the second layer. Then there is the third layer. So different layers. And also there is a horizontal as well as vertical mixture of the different layers, the different materials. So this is actually a super lattice. Oh, sorry. So I don't have any vertical. So this is the multi-layer. The third one. The third one is a quantum wire. Or you can also call it a nano wire. It shapes something like this. And lastly, you have got quantum dot. Or nano dots. Here you have actually a mixture of everything on it. You have different layers, like in the super lattice, and in the vertical direction also you have different materials in the horizontal direction. So that actually makes it so there is confinement in all the three directions. Here the confinement is in two directions. Here the confinement is in three directions. In the previous case, the degree of confinement actually keeps on decreasing. So what you have is there is a, you consider the dimension and so degree of confinement and degree of freedom. So if there is a bulk material, ready material, it has got 3 degrees of freedom x, y and z and 0 degree of confinement. If we consider a film, a nanofilm, the degree of confinement is 1 and degree of freedom is 2. If there is a wire, again the degree of confinement becomes 2 and degree of freedom becomes 1. And if it is a dot, then degree of confinement is 3 and degree of freedom is 0. So these are the 4 structures possible in case of these are the 4 structures, and in the case of film we can actually have 2 types of film. One is a single film that we have seen, and there is a multi-layered film. So this is a film, single layer, and this is, as told, this is a super lattice. The multi-layer film is a super lattice.